Our next speaker is Sir Charles Schultz. He's originally from Seattle. He lived in Orlando, Florida since about 1978. Now he's in New Mexico working on some projects. Much of his life was working in weapons and aerospace, but he did so without a degree. He's self-taught in physics and math and engineering. Right now he's working more in the direction of artificial intelligence and robotics. The Sir came into his name because he was knighted in 2000 by the Baron of Balquhane in Aberdeenshire. I hope I got that right.
It's fine, yes.
And he also won the Young Genius Award, which was a grant to do humanitarian research. So let's please welcome Sir Charles Schultz.
Thank you. Well, I don't have a model to bring today because mine weighs about half a metric ton. And I think you'll appreciate that. As it says, it's an overview of coming technologies and of the bias towards solar thermal. This is what I've spent the last 9 months on, a little project that I think you will all greatly appreciate. The concept is we want to be able to produce a lot of energy. Now, just a little bit of introduction, some of the things that I've worked on that led to this particular invention. A lot of my work was in aerospace and weapons systems. I built custom robots for Disney and Epcot. I did a lot of work with the Science Center and the Planetarium in Orlando, built laser systems and optical effects. The physics, electronics, rocketry, and robotics courses that I've taught to young people because they have a particular bent in science, and children are actually natural-born scientists. Many of them learn a lot until we beat it out of them. And the 5-year research in robotics and AI. Now, my first thought when I got out of weapons systems was, what can I apply this technology to? And so it was just a natural outgrowth of the things that I had learned in physics and mathematics and electronics based in weapons to see what I could apply to energy and sustainability. If we can make a space station that keeps people alive in orbit for months on end, we obviously have some pretty good recycling technologies. We have more resources and energy on the ground to deal with, and therefore it should be much easier if we can apply that same sort of technology to our living, our daily living. Sustainable technologies extend our abilities to survive on a limited amount of resources. We can do more with what we have, and that's one of the things that we all have basically a responsibility to do these days. Smarter use of materials means we can do more with what we have, and smarter use of technology can make more available for people. So this was a chance to turn some of the things that I had had expertise in into something that we can all use on an everyday basis. I lived for a while off the grid in what's known as the Angel's Nest, which is an experimental prototype off-the-grid home that's in Taos, New Mexico. It's technically about 7 miles northwest. And everything you see, its own wind, sun, and water power everything. It gathers water from the environment due to rain catchment. It has its own water pumping and purification. We generate most of our electricity through photovoltaic panels, and wind power also plays an important part as well. And so this was a good place, a good springboard to start experimenting with some of these technologies. How much sunlight strikes our Earth every day? Every moment, 274 million gigawatts. Think about 274 million nuclear power plants all running simultaneously, continuously. That's how much energy that would be. That's just sunlight striking the ground. If we could harvest a small percentage of that, we'd never run out. So of all the solar technologies, solar thermal, which you may or may not have heard of, is projected to have the greatest growth over the next 5 to 10 years. Now the concept in solar thermal is very simple. We simply gather heat from the sun. Sometimes we concentrate it, sometimes we don't. Many people have solar water heaters because who wants to pay to heat a swimming pool, particularly in the winter? Most of the parts for solar thermal have the great advantage of being commonly available. So we can go down to the hardware store, we can go down to Home Depot or Lowe's or whatever, and we can buy almost all of the components we need to build a solar system that runs on solar thermal principles. And so what I have done is outlined a little bit of the different technologies that will come up and how you can use solar thermal and what we've developed that I think you'll be very excited with. Now, solar heating for water, 25 to 30% of the energy that you consume in your home goes to make hot water. And when you stop and think about it, that's a staggering figure. And most water heaters, as you know, if you turn the power off in 2 to 3 hours, the water's cold again. They're very poor insulation, those systems. There are a lot to be done right there. Radiant heating applications. From 40 to 50% of your energy, particularly during the winter months, goes to climate control in your home. If we can provide process heat that's free or a result of the process of generating power from solar thermal, then all of that can go into heating your home and you don't have to spend a nickel on the electricity. Electrical power generation, that's really the big issue, because everything we have runs on electricity. Obviously, if we can find an easy, simple method that doesn't cost a lot to make electrical power, and you can put it on your home, then you can eliminate virtually all of your utility bills right there. And that's what I'm going to demonstrate to you. Purifying and distilling water. Now, that's not so necessary in this part of the world, but in many places it is. There's the major problem in the world of a lack of clean drinking water. And if you think about it, all agriculture depends on clean water. Water is the one thing that determines where we can live on this planet, or anywhere else for that matter. So if we have plenty of water, we've got it made. This technology can be used to produce drinking water. So I'm going to cover 5 different types of solar generating technology just briefly. And photovoltaic is something that everybody is familiar with. Solar cells, basically photons of light from whatever source, typically the sun, strike the cells and they knock electrons free. And those moving electrons are the current that you use to power things. Now, most photovoltaics are from 5 to 10%, 10 to 20%, depending on the technology, efficient. And they're very expensive. It's $5 to $8 a watt, typically, just for the cells. Now, for any alternative energy system, you obviously have to have the means of converting that DC into something you can use, AC power. You have to have a means of storing it. And in many cases, if people are on the grid, they'll sell their excess back, so they have to have a grid interconnect of some sort. So the $5 to $8 a watt is actually a tip of the iceberg. I know a fellow who spent $70,000 on a solar photovoltaic system for his home. And that was for the batteries, the converters, and everything. And it's a huge amount of money. We need to really cut that down before it becomes practical. Thermoelectric. Some of you may have heard of this. Just as photovoltaic can produce a current, thermovoltaic, or heat-induced current, is also useful. The problem with thermoelectric converters is most of them are made from very rare, toxic, and expensive materials, and they have a very limited range of temperatures that they'll operate over. In effect, you have a number of semiconductor junctions, the little P and N sections in here, that act like diodes. When there's a difference of temperature from one side to the other, it causes electrons to flow through these semiconductors and produce a current, similar to a battery, similar to a photocell, a little bit different material. These are also seen as Peltier coolers. If you've ever seen the little electric coolers that have a fan that run on a battery and have no refrigeration pump, they keep your drink hot or cold. It's the same principle. Solar thermal, as I mentioned earlier, I have a particular like for, has a lot of expansion that it can do, and a lot of technologies in the solar thermal arena have already been applications for many years. What we have done is take this to a whole new level. All kids love magnifying glasses, and they love burning things with them. We've just taken it to an extreme. This is our prototype solar thermal array. We gather about 14 kilowatts from sunlight, and they do wonderful things with it and make electrical power, and I'll demonstrate that in just a little bit. Solar fuel cells. Many of you may not have heard of these. Most fuel cells are based on a membrane that typically has a rare metal such as a platinum catalyst or some other platinum group metal in it. They introduce hydrogen and oxygen or some other type of different fuel that takes an oxide or oxidizer and a fuel such as hydrogen or methanol. And the hydrogen migrates through the membrane. It's called a proton exchange membrane. And it combines with the oxygen and produces a little electric current, just like a battery. It also exhausts, for instance, in the case of hydrogen, drinking water. On the space shuttle and the space station, they use hydrogen fuel cells to provide electrical power and hot water, which is clean enough to drink as part of the operation. The only thing is it's distilled, so you have to add minerals or something. The solar fuel cell is a little bit different. The solar fuel cell takes a little bit of electrical current to get it started, and then it uses focused heat from the sun to produce hydrogen and oxygen, and then recombines them with that proton exchange to make a current. So effectively, you're taking the heat of the sun, you're dissociating water, and then using that dissociated water to generate your electricity. So there are a couple of steps in the process, but it works just like a regular fuel cell. The advantage is we're using raw heat from the sun to drive it. And once it's started, you don't have to keep the little electric current on it that gets it started in the first place. It's kind of like a starter motor on your car. Nanosolar coatings, this is a really up-and-coming material. They have materials that are based on the scale of the molecule. I don't know how many of you know how big a nanometer is or what nanotechnology means. You can picture a meter, which is a little bit more than a yard in length, and you can picture a thousandth of a meter, which is a millimeter. And if you were to take that millimeter and break it into 1,000 smaller pieces, you'd have a micron or a micrometer. And if you were to take that micron and break it into 1,000 smaller pieces, you'd have a nanometer, 1/1000th of a meter. That's 9 decimal places over. How small is a nanometer? 10 hydrogen atoms, side to side, would just fit in 1 nanometer. So when people talk about nanotechnology, they're talking about things made on the scale of the atoms, or just small clusters of atoms. Nanosolar coatings take advantage of the very special properties of materials on that small scale. Typically, particles in the coating or paint will ring like a bell or a tuning fork in the presence of the right wavelengths of light. This property can cause electrical current to be created, and you have effectively made a sort of photovoltaic or solar cell out of these nanoparticles. And the efficiencies can be quite high. Some people project they could be 40 to 50% or better. The electrons are being knocked free when these little nano wands are waving about like tuning forks. And the way that it works is very, very interesting, because if anybody knows what resonant vibration is, and anybody who knows anything about Tesla has heard the word resonance, if we have 2 tuning forks that are precisely at the same frequency, and we set one in motion, its oscillations will be carried through the air to the second tuning fork. And because it is at the same frequency, the oscillations will build until they match, and both tuning forks will ring in resonance. They're exploiting a similar trick in nano coatings, where the light waves are of a known wavelength or energy, and the little tuning forks have the same wavelength. So you have a spread of tuning forks on the nanoscale, and they cover the band of optical and infrared and ultraviolet, and they absorb some of that energy and convert it to electric current. So they're little tiny tuning forks in essence. Now, of all of these technologies, only one of them you can make in your home, and that's the solar thermal. And I like simplicity. You've heard of the KISS principle. Keep it simple, stupid. Anything that you can make from common parts, anything that the backyard redneck can fix under his tree, that's a good thing. Because with solar thermal, you don't need a silicon foundry. Photovoltaic cells are wonderful things, but they require very high-tech material to make them, very high-tech equipment. And they produce a great deal of toxic materials in the process, which is something you don't typically hear about. Thermoelectric is very similar. Again, though, it requires toxic materials and specialized machinery to make it. When we look at the solar fuel cells, they sound great, but you have to have specialized membranes and, again, specialized materials. Nanocoatings, complex chemistries. Unless you have a degree in chemistry and you know a lot about molecular engineering, you're probably not going to make a nano coating anytime soon. It's not like Jell-O. Solar thermal, you can make from parts from the auto store, parts from the hardware store. Now, how can we harvest power from the sunlight? Typically, we have to collect that energy and we want to concentrate it, usually. Not always. If you have a solar pool heater, you don't really concentrate it, except sometimes there's a glass plate on the top, so you use the greenhouse effect to trap the heat in the collector and drive the temperature up. We have to convert that energy into a useful form. We like electricity because it's so versatile, it can run anything. We have to minimize our losses, and this came and bit us, and I'll explain why, and you'll see. Losses in a system make the efficiency go down. And every time you have a step of conversion from one form of energy to another, you have a loss, because nothing operates at 100%. There's always a loss. If you have a motor running, there's friction in the bearings. It's creating heat. There's vibration. There's noise. And all of that is taking a portion of your energy away. We need to recover any waste heat in our operation, and we had a very simple way of doing that. The first one that I built was put together in my garage workshop, and it came from an idea, from a science fiction story, which I won't go into in great detail, but the concept was collecting a great deal of sunlight, focusing it into a very tiny area, and using that high-intensity heat to create power. So I made this large solar lens from an old big-screen television. The big-screen televisions use typically 3 guns, as they call them. There's a red picture tube, a green picture tube, and a blue picture tube. And each of them is projecting one fraction of the image. And through this lens, those images are combined to create the white light or full color image you see on the television screen. So I happen to have a family member who works on big screen televisions, and he gave me a lot of these lenses, and I found some more as scrap plastic for $2 a piece in one of the local junk stores. Well, I bought them all. This was the first version, very primitive, but it had the capability of melting brick and boiling steel. We hit focal temperatures in excess of 3,000 degrees Fahrenheit on a clear, cloudy, non-cloudy day. Can't say cloudy, non-cloudy day. The second version, because I like to melt things like most people, was my research solar furnace. And the research solar furnace had about 1.3 square meters of area. Now, that's significant because the amount of area that you capture sunlight energy in is going to determine ultimately how much power you're going to get. We generally get a little less than 1,000 watts per square meter from sunlight when it's noon and the conditions are just right. Usually it's a little less than that, but we can be generous. There is also some loss in the plastic itself. It's not perfectly transparent or we wouldn't be able to see it. This was my second generation, or research furnace, and you'll notice that there are a couple of oddball-shaped objects in here, counterweights in the back, and there's also a reaction vessel made of stainless steel that's mounted in there. I could place lawn clippings, whatever I wanted in there, seal it up with a quartz window, and raise it to about 1,100 degrees centigrade over the period of about 5 to 6 minutes, depending on how much mass we had. And I did some research in converting biological trash into fuels, such as yard waste. You can take the bones and the skin and the leaves and all the things from your kitchen and your yard, you put it in the container, you seal it up, and you heat it to very high temperatures, and it pyrolyzes it, it breaks it down. And if you add a little bit of water, or better yet, a little bit of hydrogen, it undergoes a process called reformation, and it becomes something that is a crude approximation of oil. It's not as simple as just burning the stuff, but you can reform materials with essentially free energy and make a fuel out of it. I didn't really follow that up as completely as I could have because there were other very exciting things happening, but I'm going to get back to that eventually. And we're not advancing. Oh, there we go. If you have a 1.4 square meter lens, and that's what I'm using in my big generator, you're getting about 1.4 kilowatts, roughly. The focal spot is 1 centimeter across for something larger than a meter, considerably larger than a meter. We can hit 5,000 degrees Fahrenheit with these lenses very easily. It will boil steel, it will melt stone. We had a lot of fun making lava out of rock, and I got a number of scars here and there from improper handling. The potential to put heat into a working fluid and do something useful is there. Obviously, if you have that much heat energy, you can do something with it. 960 watts times 1.4 meters square gets down to a density of 13.4 megawatts per square meter. This is on par with the Star Wars laser weapons that you've heard so much about, the SDI project. We're dealing with energy densities great enough to cut through steel and melt brick and turn things into lava very, very easily. So it's dangerous, but we've got a couple of safety measures that we've taken. This is a brick being melted, and the black spots you see were molten glass. The brick has fused into glass in all of these areas, and the focus is so bright, of course, it washes out the camera. This was a demonstration I used to give to people from time to time, just to give them an example of how powerful the sun is. I would also take a coin from them, put it at the focus, and literally boil the metal in the coin. It takes about 25 seconds or less to boil a US quarter coin. Conversion. How do we convert it? The first thing we can do is transfer it to a working fluid. Working fluid is any sort of a fluid that will carry your heat from point A to point B. Now, water is a good choice. Various types of oils can be a good choice. Molten salt is one of the ones that many of the places are researching now. You'll see a number of solar thermal research or pilot plants going into operation shortly, and they're all saying, hey, we're going to use molten salt. The idea is, salt is actually pretty inert in stainless steel tubing, and once you get it to the point where it is molten, you can pump it through there like any other fluid. The upside of it is a 5-gallon bucket of molten salt contains enough energy, in theory, to run your household all night long. So it's a cheap, easy storage system, but it doesn't work on small scale. Understand that if you spread something out, it loses heat much more rapidly than if it's in one mass. This 5-gallon bucket of energy only works well if you've got a few thousand gallons of it all in one place. And so the pilot research plants that they're building for solar thermal typically will use molten salt for storage because, again, it's fairly cheap, it's easy to do, And all you do is you run a heat exchanger with water through it, and you get steam that can run a turbine. Water flashes into steam and creates high pressures, and that high pressure steam can operate vanes in a turbine, pistons in a steam engine, or whatever you wish. Or if you're just interested in heating, you can run a radiator with it very, very easily. Oil can carry the heat to another location, and that's another means of storing energy that actually can be quite effective. Oil typically isn't very expensive. The only drawback is when you hit above 450 to 500 degrees Fahrenheit for most types of, let's say, motor oil, they will evaporate. They'll hit their flash point. So we did some experiments with motor oil, and we had to pump all the oxygen out of the system. Otherwise, we would have a terrible mess because it would have ignited inside the heat exchanger pipes. And you learn a lot of things when you're doing research. Now, the concentrated light might be able to be moved from one point to another very easily, and I had this brilliant idea. Obviously, when we tried it, it didn't quite work as planned. You see, the idea was to construct an array of Fresnel lenses. They could be small, they could be whatever you wanted, and the focal spot from every one of those lenses would end up in a fiber optic bundle. We would route the fiber optic bundles together and run them to our target area, and all of that sunlight from all of that area would be concentrated to one spot. Instead of having to have a humongous lens, we can buy $1.50 page magnifiers. Wonderful concept. And primarily it did work. We were able to achieve ignition at the other end of a light fiber. My reasoning was simple. You go to the radial keratotomy place, they slice your eye up with a laser, it's gone through a light bundle. They do a little surgery with a laser, it's through a fiber bundle. The problem is, those are very specific types of light fibers, and we'll get into that in a minute. So we went out and ordered a bunch of plastic lenses. We built these wonderful aluminum frames for them that were articulated, and we made a tracking array out of them. Very simple, very clean. We've got 20 little lenses there, each gathering about 70 watts of power, 1,400 watts. Not bad. It's all made of aluminum, and we made some little tracking hardware. I put some stepper motors together that digitally controlled, could swing each axis around and track the sun. Very easy. And that messy place was my workbench there at the time. Now, the problem we hit was excessive power density. Obviously, if you can boil a quarter, fiber optics are destroyed too easily, and that was our problem. Plastic and glass fibers melt or vaporize, and the reason is very simple. They are not perfect conductors of light. If you spread out the spectrum into a big chart, you will see peaks and valleys in the different colors, the different wavelengths, and some of those glass absorbs wonderfully well, much to our chagrin. Sapphire fibers are typically used in laser and high energy applications or other types of specialty glasses or minerals. We really couldn't put a bundle of sapphire under every one of our lenses. We're right back out of the cost-effective area. Nobody wants to buy something that costs more than photovoltaic. Cooling at the time we didn't pursue, and afterwards I thought, we could have put these things in a little container, put a cooling fluid inside it, and a heat sink, and voila. It would have worked. Probably. Not sure. I think it would. But we could encapsulate the fiber ends in a cooling system, and then we could transfer our energy into it and wonderfully run all of our fibers down to a boiler or whatever we wish to burn or destroy. And we could end up with all that energy concentrated very, very easily. And we will do some more experimenting with that because it eliminates a lot of the steps of transferring energy from one point to another through transformations from liquids to other materials through heat exchangers. If we can get rid of that, we can make it cheap and simple. Alternate heat collection methods. The thing you see there is a copper pipe that has a flash boiler in it that I constructed. We went ahead with the oil as a transfer fluid. Oil's cheap enough for that sort of thing, and it gets recycled. You're not burning it up. So we made our tracker cycle oil and run that heat into this little reservoir, and we'd run water through the coil and flash it in theory. And there's the working multi-lens tracking array. And you can see we had some very interesting plumbing to do, and when we did that plumbing, we had individual heat collection pipes under each linear array of lenses, And we even put blackened targets of copper on each one with heat sink compound to transfer all that energy in there that we could get. We were going for every bit. We have our oil pump down here, and notice the oil pump is pushing the cool oil in, and the hot oil goes back into the system. And there's a good reason for that. Try and find a small DC-powered oil pump that doesn't melt. Now, hot oil we can store overnight, and there are very simple methods of doing that. Use what's known as a vacuum flask. You have a vacuum-insulated container. Many of you know it's a thermos bottle, or a Dewar flask if you work with cryogenics, such as liquid nitrogen. Well, it works either way. You can store very hot materials for an exceedingly long period of time. You could, in theory, keep your water heater hot for 3 or 4 days if you simply vacuum insulated it. Think of the savings there, if you can afford a vacuum bottle for it. Steam and raw heat you could then extract on demand. Well, we can run our hot oil into this reservoir, we can run our water through our steam collector, flash it into power and use it for whatever we want. That's a wonderful idea. And it's easy to store some oil, let's say, in the back room of your house somewhere in an insulated container. You never have to see it. It acts as a battery. There's no lead, no acids, no hydrogen venting when it charges up. You don't have to check the fluids every couple of days. It eliminates a lot of problems if you can make it work. But then there are problems, and they can be overcome. But again, it becomes a question of cost. What are you willing to pay for it? Raw heat can provide hot water or radiant heating for the home, and I keep going back to that because I did live off the grid for quite a while, and we were able to do some of these things quite effectively. So we decided to design a system that would use that concept. This is an alternator that we modified. If anybody knows anything about alternators, they generate power in your vehicle to charge the battery and run the headlights and do all those wonderful things. We didn't like the idea that you have to provide 12 volts of power to make that happen. So we ripped the core out and we built a new one with permanent magnets in it, super magnets, and now it's a magneto alternator, so it doesn't need a drive current, it'll run on demand. Then we had a small turbine which was designed and machined in a CNC shop. And my very good friend Joseph Holden, who has the patent on the afterburner for jet engines and is an excellent aeronautical engineer, designed this turbine for us. So it's very compact and it's rated at 12 kilowatts if necessary. This is the condenser and heat recovery system. After all, we have live steam going in, we've got to have something coming out, and a lot of it. The condensate carries a lot of heat energy. So we put a flat plate heat exchanger in here, and we can recover the waste heat back into our water tank. We just cool it enough to be just below the boiling point because we don't want to take all the power out. It has to still convert it back into steam to go through the cycle again. And this is a standard off-the-shelf water heater anybody can get. Again, we like off-the-shelf. Pitfalls. This is a pitfall alert from someone with experience. Number one, just because you can make something yourself, it does not mean that you should. Well, I can drill a hole in that and weld a piece on and waste your time. Go to the hardware store. My goodness. You know, your time is the single most valuable thing you have, and to waste it is the greatest prodigality, as they say. Put your time where it belongs. Buy stuff. Don't make things. If it sounds like a good idea but nobody's doing it, there's usually a darn good reason. They've run into these things, and they know. And a lot of people have lost a lot of money and a lot of hours and torn their hair out over these things. They know. Pornell. Jerry Pornell is one of my favorite authors, and he writes a lot about futurism, and he writes about advances in technology, and he's science fiction as well. And he has his first law of business, which he says, everything costs more and takes longer. Yes, it does. And from this, I'm going to sum it down to science is not exempt from Pornell's first law of business. You will find that great ideas really aren't in many cases. You have to pursue things properly. You have to do the math. You have to do your homework, or you waste your time. There's no question about it. So, how did I get my high-temp oil pump? Well, I made it. And yeah, it worked, but not as well as, let's say, a gear pump, which I could have bought. And I did end up shelling out like $600 for a gear pump. And all the while I'm thinking, my God, we can't sell things with $600 parts in it. Nobody could afford it. But the proof of principle here was the important thing. We had to show that it would work or not. So, here we go. Why do we track the sun? Here's another good question. You know, most solar systems just sit there. But there's something called Lambert's cosine law, and I'm not going to show a whole lot of math. If people don't like it, they look at it and go, yuck. Lambert's cosine law very simply states that the amount of illumination on a surface is proportional to the cosine of the angle striking it. You can ignore this stuff. Basically, if it comes head on, you're going to get all of it. If it comes at an angle, you're going to get part of it. We want a system that works partly. Why do we use very high temperatures? This is another thing I keep coming back to. I talk about the high temperatures here, and there's a very simple reason. In any thermodynamic system, any system with heat involved, and just about any system actually, if you start from low differences in energy, you get low yield. Sunlight is wonderful stuff, but we can concentrate it very easily and it becomes even more wonderful. So if we can raise our temperatures, we can raise our efficiencies amazingly high. We are now getting a measured transfer between 84 and 90% of our incoming sunlight energy into the system because we did our homework and we experimented a lot. But we got to that point. We can get a huge amount of our efficiency because of the high difference in temperature. Our initial tests were positive. That sounds so good. Our array went together flawlessly, and that was true. And yes, this is duct tape holding the lenses on. We went through a lot of, how do we fasten hundreds of little plastic identical lenses with uniform tension? And you know, we scratched our heads and we thought about folding strips of metal and buying little clips and drilling hundreds of screws, tape them. Then we mounted our turbine with a steam expansion chamber. Anybody who works with turbines knows you've got to have an expansion chamber. It acts kind of like a capacitor or a shock absorber. It evens out the flow. It allows it to run smoothly. So this is our steam expansion chamber. And all this is just copper. This is it's a version of stainless. I'm not certain what the number, it might have been 4140 or something, I'm not really sure. The oil reservoir and pump. We're moving along. We have our system for gathering our sunlight and pumping it. Now we have to put it somewhere. We have our turbine, we have all the goodies. Here's our high-end oil pump and a filter. Never forget the filter. If you munch some metal parts, you will munch it all. And this is a welded steel tank, which we had some insulation for, and that's where our oil went. And the reason for all the plumbing on here is, again, we had to pump all the air out because we knew that if we went over certain temperatures, it would explode because it would flash. Quick video. This is when we first put the array in operation.
Today, we've already circulated oil through it. Just in a static test, sunlight raises the temperature of our electric pipes over 180 degrees Fahrenheit. As soon as we have the sun striking on this on a continuous basis, we should be able to generate 6,000 watts of electrical power and heat waste power as a result.
So that's just a brief clip showing the array when we first commissioned it and did our earliest tests, and we got some very encouraging numbers out of it. It looked really good. The heat collector pipes, which you see as the black objects, are actually heated to temperatures between 700 and 1100 Fahrenheit by the sunlight. The problem. It went ultrasonic. So we had a wonderful system for gathering heat. We had a wonderful system for converting it into steam and a wonderful turbine that would recover it and turn it into something we could use, spin motion that'll run a generator. That's what we were after. We just want power. We don't care how we get there as long as it's cheap and it's easy. So far it doesn't look either one of those things, but all prototypes are more expensive than what you end up with on the shelf at the store. But the problem is, for the area of lens we had, the area of pipe was too large, and we were radiating heat like mad. We were just wasting buckets of heat everywhere. The heat was just leaking out of it like a sieve, and we couldn't stop that from happening. But we didn't let that deter us. and this is more a journal actually than a, than a real expose of the technology. And I've got a couple more video clips showing some of the testing. Our others have a little better quality.
Okay, air pressure on.
As you can see, every piece had to be tested and integrated into the system. We don't want to wreck a lot of hardware and waste a lot of time and money. So we test our turbines, we test our generators, we test our lenses and our tracking, and then everything gets integrated very, very carefully, a step at a time. You know, diligence and care. So even though the initial testing was excellent, the turbine spun, excellent transfer energy, heat was being collected, the collector pipes got very, very hot, and the tracking hardware was working. It was following the sun, and we thought, this is it. We've got it made. Not so. The system failed to work. It failed to work. The lens area to the pipe area, as I mentioned, was too great. The ratio of the lens was too small to the pipe area, and so we were losing our heat all over. The oil did go just below the boiling point, just tantalizingly close, and we were like fanning things, come on. But it didn't get there. And we couldn't figure out why. We had all this power. Where was it going? So we had one of those little thermal probe heat guns, and we started measuring things and going, oh gosh, now what? Because let me tell you, fiberglass insulation is horrible stuff. It really doesn't work. Not very well at all. So we had to analyze our failures and regroup, because we couldn't get insulation that was effective enough, cheaply enough. It would have cost too much. And again, we're looking at what's it going to cost you to get this thing? So we wanted to test our direct steam principle. We wanted to do some small tests with little boilers and turbines and see what we could do, see how well it worked and get some measurements. We wanted to refine the tracker because, as it is, you have to keep that spot directly on your collector. If it wanders a little, things bad can happen, bad stuff. As it is, we're basically talking about lightsabers slicing through your hardware. And it really did. It got really nasty. We had to test various generators and see how they would work with our turbine. We had to look at something called coupling and transfer efficiencies. And we had to design a more effective collector system. So I made a tiny boiler, not much larger than your thumb, and a tiny spinner, and I tested the system, and I got some real-world data out of it. That's what we really need, because that tells you where to go, what's going to work and what isn't going to work.
This is a new compact turbine, but again, this is just made by the polyethylene. It's a small model, 50 inches across, you see. I've clamped it in the rotary table on the machine, so I can just blow the layer quickly, and we can do a quick look at how it operates under compressed air.
That fellow's only about that big. And it was made of plastic, but it was simple proof of principle. And it's a single-stage impulse turbine. And notice how nicely it was balanced. Okay, I like to gloat a lot about good hardware when I build it.
So you probably want to kind of spin it out very, very good, and the balance is almost perfect. So this is a small turbine that took a couple of days to put together on a little handmade, on my little hand-operated machine there.
And that's a homemade mill with stepping motors, and you can basically make whatever you want with computer control. I grew up poor, and so you learn to make a lot of things. But again, don't make things if you can buy them. So this was a small turbine, which I later duplicated in aluminum and in other metals, and we were able to make small spinners, and we were able to make compact systems with a single lens. A boiler, a spinner, and a generator. Single lens solutions that make a couple of 100 watts. Now, you know, something like that could be very useful all over the world. And that's one of the things I am going to pursue, making single lens solutions. And consider, if they're cheap enough, you can put 2 or 3 or 4 of those in your backyard or on your roof or whatever, and each of them is contributing a little power. And they're self-contained, and they're closed cycle.
Okay, we're at 158 psi on the input line. Our previous test got 140 volts DC
And you'll see that light is coming on very easily. The generator is the small cylinder at the end of the assembly right here. Now that funny disc,
Okay. 140 volts. So, setting up.
okay.
Very good. Very good.
So the little disc on the end is a tachometer that I put together so I could track the movement of the thing, just a disc and an optical sensor. But again, every step of the way, we tested our generators, we tested our boilers, we tested everything, and we used sunlight to pressure test our boilers, and we exceeded 450 psi very, very easily. And this was because we increased our insulation, we increased the transfer of that light into that boiler, special design of the boiler itself as well. This was my new toy, and this was a self-tracking, basically death ray. The sensors here consist of a pair of photosensors and a shadow strip in the middle. And the greater light drives the motor in that direction. Simple enough for this. So I've got one for the x-axis and one for the y-axis, or the azimuth and elevation. And you may notice with a start that these are window motors out of an automobile. Cheap, off the shelf. I began to follow my own rule there. The brain to operate it is in the box down here. And basically all this does is track the sun so I can put my test hardware in that bowl, which is an insulated stainless steel bowl packed full of spray foam, and that I can keep the temperature up and I keep the wind from cooling off, because wind loss actually was a big detriment to a lot of these experiments. At this point, we have a system where we can put some small test hardware together, walk away from it, and it'll run for an hour. And you need things like that. So then, we went on to, we did. Okay, the new unit, we designed our large collector. 10 1.4 square meter lenses, 10 steam boilers, one at each focal point of each lens. A large tracking system, and the single steam plumbing system. All of the steam goes to a single point. Everything is insulated. A large redesigned tracking system for the elevation and azimuth, and I'll show you how large in a moment. And it's designed to handle large wind loads. Because of its excessive size, we knew that with the sorts of burst winds we had, it could break it. So everything was made of steel. Of course, now, when you get a system like this commercially, and it's going to happen soon, I'll show you the results, it's not going to be anywhere near as large, because we'll have shorter focal lengths for our lenses, and a lot of those things will have been taken into consideration, making it small and efficient. I needed a drive system to move it around. I bought a wheelbarrow wheel, some motorcycle chains, some hubs, and a big DC motor, and I built that. Installed and testing it right there, we measured at 12 volts only about 2 amps of current moving over 1,000 pounds of load. I later tested it with 4 AA batteries, and it actually moved at half speed quite effectively. So we were able to move roughly, I think it was 1,100 pounds altogether, half a metric ton, on 4 AA batteries on the circular track. That's how well balanced it ended up being. These are some different shots of the beast, and this is our 14 kilowatt model, and it was constructed at San Juan College in Farmington. It's kind of an out-of-the-way place. Not a lot of people go there. We didn't have a lot of publicity or gawkers, and it made it very easy to do the work. The downside was there was a huge industrial 440 compressor just a few feet from my workbench, which I cursed soundly on a daily basis. Initial testing with boilers in place. You will see that each of the cups inside here is in it's a steel box, and it's got fiberglass insulation. Our water injection system is here to put pressurized water in. Remember, if you're making high pressure steam, you have to have higher pressure water going into the system. Well, they wanted like $700 for a water injector pump, and I scratched my head and I thought, if you get one of those little tire inflator pumps for $35 at the auto store, it'll exceed 200 psi. I filled this pipe with water and put an air head in it, and the pressure of the air from that little compressor injected the water for our tests. Very simple. That worked out well. Now, each of these boxes is steel. It's got fiberglass insulation and a single boiler inside it. And we did our testing, and we found, number one, it slices that insulation instantly when the sun touches it. It was messy, but fun to look at. this was my refined sensor. Again, precision was the key here. I had to keep that beam right in that cup on all 10 of those things. And so every one had to be adjustable, and every one had to be precise. I solved the problem by making a 3 light sensor device. The cell you see on the left has an identical one on the right. It measures the differential just like the previous one, and it tracks it. But the slit in the middle goes to another smaller sensor that is only active when that light is dead on the center. Now, I can tell the computer that I built that's running this thing, when you see that lock sensor, stop. Stop. And if you lose it, track in the direction the sun's moving just a little bit. And it was very simple. The control system I built in a 12-hour marathon from scratch. A pair of PIC processors, and some of you with electronic experience will know what that is. An X and Y input for the elevation and the azimuth. And inside the box, there's an analog section which takes the I signals from the light sensors and converts them to digital here. A little calibration so you can set your exact sensor speed and sensitivity. A pair of microprocessors that are identical, and I chose to use 2 for one very simple reason. If you've got a problem on one axis and there's one processor, you can't troubleshoot anything. This way you can swap the chip and see if the problem moves, and you can know in 5 minutes what's wrong. Output relays, simple relays. You turn them on, you turn them off. This thing is big and cumbersome and slow. You don't need speed control. Why so much precision? Again, this focal spot has to be within a 2-centimeter radius in the center of that boiler. The heat flow has to remain uniform for that generator to run uniformly, right? If it gets cold or hot, it's going to change operating speed. And the sunlight's burning through the 1/8-inch steel cover plates. We put cover plates over the insulation because we didn't like seeing melted insulation, and the sun didn't care. It burned right through the 1/8-inch plates. I may have a picture of some of those. Ah, yes. This is what happens to the steel plates when the sunlight strikes them. It eats them. Every plate looks like it's been run through a masher. But it gives you a little bit of an idea of how much power we're with. We had success. We generated over 30 bars or 450 psi of steam pressure in a huge volume. Our operating temperatures for our boilers exceeded 370 C regularly, about 700 degrees Fahrenheit, continuous. And we had a steam volume you wouldn't believe, and I've got a video of it, and the closed cycle operation will recover all that waste heat. Now in the prototype we didn't have the closed cycle thing. It's a little hard to get all the details working. You want to verify that your basic principles work, and that's important. Final results, and I do have a video here. I think I have the video. I could be wrong. I've been known to be wrong. Okay. In this particular test, we discovered something about our boilers. We made them out of copper, 1/4-inch thick copper, which is wonderful. We pressure tested them. They were great. When they got hot, they got soft. We exploded a lot of boilers, guys. Fortunately, they were in steel boxes with these nifty warped plates, and the fragments and shrapnel didn't go very far. So, I have a spin-up test video. Don't worry about it. I can talk for hours.
Charles, was it on that menu that we saw?
I believe that it was, but again, I could be mistaken. It should be like 1163. Okay. Anyway, the idea was we wanted to refine this into a product that you could use and have success. We did have pressure, we had steam, we had our spinning turbine, and we had electricity coming out. And that's what really matters. So now it's just a matter of refinement. We know it works, and we've demonstrated it, and we've actually had a group of people from Sandia National Labs, 4 scientists who came out and said, man, I wish I had your job. No, that's not it. That's one of the larger generator tests. That was our 10 kilowatt generator test.
Okay, we're just about setting on our boilers.
There you go. That might be the one. No, that's one where we burned through something.
Okay, we're just about setting on our boilers. Sunlight's coming up and hitting that cloud.
We had a cloud, that's what it was. You know, the bane of solar energy, the cloud.
157 PSI, we have new 1 horsepower. It's going to start anyway.
Yeah. Well, no, but don't worry about it. We'll continue from there. That sounds great. Let's see. You know what? I don't think it's on that menu. I may have missed it. Well, my fault. We've got a couple of videos showing the thing spinning up, and if necessary, I'll load one on there. See if you can find one that says something like 08 at the end. I can see that page, yes. And I don't see the video there. I've got, nope. All right, for whatever reason, it's not there, but don't sweat it. It's not a big deal. We'll continue from where we were. We're flexible. What I will do is, if I can locate that video, I'll go ahead and load it on the cartridge so we can see it at the end of the presentation. I think you'll get a big kick out of it. Okay, great. So our final results were the system did operate, we got our power, but we were exploding boilers. So we had to do something to get over that. And what we ended up doing was designing new boilers out of stainless steel that were frequency welded, because that's the only way that we could reach the sort of pressure retention without the things exploding. Copper got too soft at that pressure and temperature range. It just wouldn't work. All right, so where do we go from here? And your aspect's off, but that's fine. We turn it into a production model. We make our new boilers out of stainless, and that's happening right now. We put new sensors and refine the control software, and I'm doing that actually back in my room. I'll be working on some of the software later tonight. And our target, $2 a watt when we initially offer it, and $1 a watt once it's in production. That's the bottom line. So, the project details. The turbine design was by Joseph Holden. He's an amazing man. He has a huge amount of aeronautical experience. He designed the thrust tube technology that's used on many of the jet fighters and aquatic vessels. Anybody who's in the military like the Air Force would know the name. The boiler design was a collaboration between Joseph and myself. I did the concept optics and electronics and a little bit of welding. The ugly welds were probably mine. The funding was by freewillpower.org, which is an organization that came up with the money for us to build these things, and by LifeSeed International Trust. So we've had a little bit of funding that allowed us to get us here. And just to explain how cheap this project was, the whole month, 9 months, both of those huge prototypes, everything you saw we did for $100,000. That's it. So, and that's that. So,
Charles, we actually have about 5 or 8 minutes to take some Q&A. Would you like to do that, sir?
Absolutely. Ask
Okay,
it.
Q&A. First, okay, number one's over here.
Yes.
Yeah. Charles, meet Charles.
Yes, Dr. Charles Osmond.
Yes,
Absolutely,
indeed.
yes.
Wonderful presentation. I have to ask this question. I'm sure there's an answer. I'd love to hear it. My first thought was, if you had less concentration of energy, went to, say, a black body collector, that would relieve a lot of the pressure requirements and that sort of thing. Why did you want to go for such a high concentration of energy? I'm just kind of curious about that. Is there a trade-off there somewhere?
Yeah, number one is the greater the temperature is for that hot spot, the more effectively that energy is transferred into our system. It's a very simple law of thermodynamics. If you look at the differences in temperature of a system, you can roughly approximate the efficiency by the fourth power of the difference in degrees Kelvin. So the hotter it is, a little bit of temperature increase means a huge increase in efficiency. Now, one thing that we couldn't really get around was the pressure. We need both pressure and volume in order to run this turbine. That's true at any energy application. And so we couldn't really dispense with the high pressures. The temperatures were inherent in what we're doing, but the stainless steel boilers, so far, the tests are very positive. Any other questions?
Okay, real quick before I take any other questions, I just want to mention there's going to be a short 30-minute section. The food's going to be here about 10 minutes after 7, and Vernon Roth, or 20 after 7, Vernon Roth's got a 30-minute presentation on consciousness integration in health and research. So actually, right after Sir Charles finishes. We're going to just take just enough time to change the DVD. We're going to try to do it again, which we were trying to do last time. We ran into technical difficulties, and I must apologize because it dragged on. But if you want to come in for Vernon's, there's just, or you can go out in the foyer and mill and mix around. Okay, we had number 2 right here, and who else was next after that?
Yeah, 2 questions.
Okay.
The pumps, are you using ceramic impellers on your pumps? for the heat?
Actually, we're using metal impellers right now, but we have a design that can be made out of Cylon, which is a very high temperature ceramic, and that's what we will be using in our production model.
All right, and where did you shop for your PC components?
The PC components, actually, you mean like personal computer components, or?
The ICs and...
Oh,
Chip.
I just bought a lot of stuff off the shelf from Mouser, and in fact, I've got another design I'm working on that cuts the part count to about a third of that. Prototypes are usually a little sloppier and make it much, much easier.
Yes, your tracking systems, did they get lowered in price quite a bit, or have you?
No, I built the whole thing myself, and right now, one of the reasons I had the 2 axes separated was, of course, for troubleshooting purposes. Mm-hmm. I now have a GPS module that will be incorporated in each of the production models, so that anywhere in the world you put it, if you aim it south, it will know the time of day, it'll know its latitude and its longitude, it'll know where the sun is because I'm writing a small piece of astronomy software that will track the exact position. So even if there's cloud cover, the array will continue to track properly. Right now, clouds can give mine a little bit of a fit.
Thank you.
You're welcome.
Yeah, let's go with Ted and then we'll go with number.
We're targeting, since we're looking at a system that will produce about 6 kilowatts of deliverable electrical power plus your waste heat as useful heat, we're looking at about $12,000 initially and down to about $6,000 once we're in production. $1 a watt, that's our target.
Quick question, what
Yes.
are you doing about sound deadening? That turbine wails.
Yes, it
I could see
does.
if you had near a house, I could see, whose wife had a problem with sound air conditioning? Yeah.
Yeah, actually, we found that once we put the bell on the exit of the turbine, almost all that noise vanished. So because of the fact that high frequencies and low frequencies penetrate materials in a different way, we found some very simple methods of eliminating that noise. So you'll hear it, but it'll be very, very low.
Okay, any others? Okay, one more here.
Yes.
For those of us who live up in the mountains, and actually our major costs are propane in the winter for heating our homes.
Yes.
This is lovely if you just keep it as a heat system. And I was wondering if you'd ever considered a model minus the electricity, minus the turbines, and just pump that hot water all through your house.
Indeed, we can. And if you are familiar with any of the normal flat heat collectors, most of them are blackened foil, such as copper foil under a pebbled safety glass cover. The transfer efficiencies for those can be anywhere from 30 to 50% typically. So you do lose a lot of heat. You don't really get but about half of the energy in the sunlight in one of those. Again, if you concentrate it, such as with a parabolic reflector or a lens, your efficiency goes up, but you're really running against cost. The big thing that raises the cost of those things today is the cost of copper. And we're trying to avoid expensive materials. Plastic ones are cheaper, the efficiencies are far worse. But some of that can be alleviated by putting the material underwater. So we do have some plans to make a system that will pump water from any source and distill it in the process and produce drinking water and heat and electricity. And we also have plans for the single lens systems that can be used strictly for purifying water or pumping water. We have a number of different products in the wings. So once we've finished, our focus has to be, of course, on this one product until we've got it where we need it. And once that's done, yes, we will be looking at heat and lighting as well. One of the things that I designed using those individual lenses with the light fiber bundles was a means of putting a skylight in your home, even in the basement, by running a little light fiber that big from the lens down to a closet or a basement or whatever. So you can put a skylight inside without cutting a hole in the ceiling, without destroying your insulation value or having any leaks, and it tracks the sun automatically so the illumination remains even throughout the day.
Ladies and gentlemen, the amazing and highly honored and esteemed Sir Charles Schultz. Thank you.
You're welcome.
Okay, we're going to try to just change that DVD real